well, thanks everybody for coming out and braving the rain. I'm going to tell you guys about the growth spurt of the early universe. So to start off, I'm going to give you the main takeaway that I want you to have by the end of the talk. So don't be afraid if you don't understand what the statement means or all the words. I'm hoping by the end that you will. So the main takeaway is going to be that gravitational waves can help us understand the earliest moments of the universe. But why is this even important? Well, if we can understand how the universe started, it can help us know how and why the universe evolved the way that it did, and why we see the universe the way that it looks like today. So here I have a picture of what scientists think the history of the universe is. Starting from the left-hand side to the right-hand side, we have time, and the size of this cone basically shows you how large the universe was at those different times. So at the beginning, lots of scientists think that it was the Big Bang that started the universe, so time equals 0. Then we have this section of really fast expansion called inflation, which will be one of the main topics for this talk. Then at about a microsecond, or 0.00001 seconds, would be when protons formed in the matter that we know today. Then we have nuclear fusion, which begins at about 0.01 seconds, and that continues until the universe is about 3 minutes old. Then if you fast forward to about 300,000 years, we have the cosmic microwave background, which I'll explain what that is in a moment. Then nothing really happens until about 200 million years, when the first stars and galaxies begin to form. And this continues to happen until we get to the universe as we see it today, at about 13 billion years old. Okay, so I'm going to now tell you about the cosmic microwave background. And in order to do that, I'm going to try to explain photon scattering, or light particle scattering. So imagine you were at a party, and you wanted to be able to walk from one side of the room all the way to the other side. Well, doing that, you're going to be hitting into lots of people and getting bounced around, and it's going to take you a really long time to try to get all the way to the other side. But as the night goes on and people start to get home and they get more tired, the party's going to look more like this. And it's going to be really easy for you to make it to the other side of the room. You probably aren't going to end up hitting a single person on your way. Well, this is kind of what happened with the photons in the early universe. We had a time where there were so many protons and electrons and neutrons, so matter particles, interacting with these photons, which makes these photons bounce off of them and go in all these different directions, and they can't get out and free scatter towards us or try to leave the room. Until a certain point where these matter particles start binding together, and the photons are able to free stream towards us. This instant in time we call the cosmic microwave background, and we can actually measure it and get a picture of what the universe looked like when it was about 300,000 years old. Funnily enough, the cosmic microwave background was actually discovered by accident by 2 engineers at Bell Laboratories, Arno Penzias and Robert Wilson. They had this radio telescope that they were using to try to measure the galaxy, and then also using for satellite communication experiments. But they had this signal that they couldn't explain. They ruled out that it couldn't be from the galaxy, and they thought, well, maybe there was something on Earth that was wrong with our telescope that was giving us this signal. And for a really long time, they actually thought that it was just pigeon poop. It must be inside this huge horn here, and that's why we have all this extra signal. Eventually, they were able to rule that out, and they'd realized that it must be from something outside of the galaxy. But they didn't really think it was a big deal. They were going to publish it as just a small little note in one of their papers, until one of their colleagues suggested that they talk to Jim Peebles, because he was about to release a paper about the cosmic microwave background that he had predicted. So they ended up talking to him and realizing that that's actually what they had measured, and this was such a significant discovery that they won the 1978 Nobel Prize in Physics. Jim Peebles actually also won a Nobel Prize last year in physics, not just for that prediction, but for a lot of theoretical work in cosmology in general. Another pretty cool fact is that you guys all have kind of detected the cosmic microwave background as well if you've ever used an analog television. So if you ever use an analog television and when you're trying to go between channels and you have all this fuzziness, about 1% of that fuzziness is actually the cosmic microwave background that the antenna are picking up. Okay, well, this discovery was really cool, and people wanted to be able to figure out what the cosmic microwave background looks like from the sky at all different parts on Earth. So if you think about it, the Earth is a globe. So if we were going to map the entire sky from the Earth, you're also going to get like a big sphere, another globe. But we like to look at data in 2 dimensions, like on a computer screen or on a piece of paper. So if you think of the globe, when people do that, they look at maps. So this is a 3D, you take the 3D Earth, and you project it down to 2 dimensions, and you have a map of the Earth. Well, you can do the same thing for all the data you collect of the cosmic microwave background, so of the entire sky. You can project that 3D globe down to 2D, and you get something that looks like this. This is actual data of what the universe looked like when it was 300,000 years old. All of these photons were at a temperature of about negative 270.4 degrees Celsius. And if you notice, there's no structure here. Everything is essentially exactly the same. And I'm going to try to motivate to you guys why that's a little strange, and why we don't necessarily expect at first that everything should be the same temperature. So imagine you were having a dinner party, and you invited 2 people over, and both of them showed up with potato salad. You could probably dismiss that as a coincidence. Even though they had thousands of dishes to choose from, it's not that strange that they both showed up with potato salad. But now imagine you invited 1,000 people over, and every single one of them brought potato salad. Not only did they all bring potato salad, they all brought the same amount up to 5 decimal places. So they all brought 1.000001 kilograms of potato salad. Well, this can't really be a coincidence anymore. They must have been in contact with each other before and decided to play this hilarious prank where they all bring the exact same amount of potato salad to the dinner party. Well, this is similar to what happened with the photons in the early universe. If they're all going to be the same temperature, they must have all been in contact with each other before. But if you remember, I told you the cosmic microwave background was 300,000 years after the Big Bang. But if you think about it, that means that the largest volume that the photons could have been in contact with each other over that amount of time is about 1 million light years across, where a light year is how far light can travel in 1 year. But that actually only corresponds to about 1 degree on the sky today. So anything above just degree patches on the sky shouldn't be the same temperature as each other, but they are. So scientists were trying to figure out what could have caused that. And one of the explanations that people study is known as inflation. So here is the history of the universe again, where it's showing you here's the Big Bang, and then there's this huge expansion. So within a fraction of a second, the universe expanded with accelerating expansion. Then you have the cosmic microwave background, and the universe is still expanding but more at like a steady pace. And it's starting to speed up again. But nothing really compares to how fast it expanded here. So that's great. Inflation predicts that everything would expand really fast, and we'd measure the cosmic microwave background all to be the same temperature. But we have to also consider physics of the small scales, or quantum mechanics. Quantum mechanics says that there has to be some amount of randomness, and not everything can be perfect. So there should be small changes in these temperatures that we should measure. And we were actually able to do that. So if you take the cosmic microwave background and subtract off the average temperature, you're left with a bunch of these really small changes in temperature that are all on the order of microcelsius, or 0.000001 degrees Celsius. So it's, essentially like everybody bringing potato salad up to 5 decimal places the exact same weight. So they might seem like maybe they're not important, it's really small. But this actually has a lot of information embedded in it. Even if to your eyes, you probably can't look at it and see any like patterns or correlations anywhere, but we can use computers to try to figure out how likely it is that different parts of the sky have the same temperature. So basically what you can do is you can get your computer to draw a line on the map with these 2 dots at the end, and then calculate what are the chances that these 2 dots have the same temperature. Then you can move the line and do that again. You can move it again and figure out how likely is it that these 2 dots have the same temperature. Okay, once you do that for the entire sky, you can then do a smaller line and try to measure how likely it is that these 2 spots have the same temperature. You can move it, try to figure that out again and again, then go to even smaller scales. And you can continue to do this until you've mapped out all of the different line sizes for the entire sky and turn it into something that we call the power spectrum. So I know there's a lot going on here, and don't worry, I'm going to explain it piece by piece. So on your horizontal or x-axis, you have different line sizes, where the largest line sizes are on the far left, and it gets smaller as you go towards the right. Your y, or vertical axis, is how likely it is that the two dots at the end of the line have the same temperature. This wavy line is the actual sky measurement, and the horizontal line is what it would look like if the temperature distribution was truly uniform. And then on the top, we have little panels of what the cosmic microwave background would look like at these different scales. So on the far left, we have what it would look like if it was about 90 degrees. So if you were going to measure the sky here and measure it all the way over here and figure out how likely it is that those have the same temperature. In the middle, it's about a 1 degree separation. So if you're much closer together and you're trying to figure out how likely it is that those spots have the same temperature. Then on the far right, it's 0.25 degrees, so even closer together. And this was actually predicted by theory, and we were able to measure it. So that's great. Inflation predicts that we should have these small changes, but overall it should be pretty uniform, and we were able to see that. But I also told you that inflation happened before the cosmic microwave background. So how can we be sure that inflation is what happened, and it wasn't something else that caused these small temperature changes, but for everything to basically be uniform? Well, we have to think of other things we can look for to become more confident that that's actually the answer. And scientists came up with a pretty cool idea. It's to use gravitational waves. So if you recall, back in 2015, LIGO, or the Laser Interferometry Gravitational Wave Observatory, detected two black holes merging. So you can kind of see what's going on the artist rendition on the screen. You have these two masses, which are circling each other, and you have all these waves coming out. So these are gravitational waves, and it's bending and squeezing the fabric of space and time itself. This discovery was so amazing, they actually won the 2017 Nobel Prize in Physics for it. Well, just like how we have black holes in our universe today that we can measure these gravitational waves from, inflation also predicts gravitational waves being produced in the early universe. And we could try to figure out how we could try to measure those gravitational waves to have another signature of inflation that we're measuring. So to try to explain how we can try to measure those, I'm first going to show you guys what a normal wave would do if it's running through a slinky. So here we have a slinky, and we have a wave moving from the left-hand side to the right-hand side of the screen. As it's going through the different rings in the slinky, it's causing them to get pushed higher or lower. So they're moving up and down as this wave is moving from the left-hand side to the right-hand side of the screen. So now imagine you just have one of the sections of the slinky, or just a circle of test particles. They could be anything. And you put a gravitational wave through it. It would look something like this. Here you have a gravitational wave coming out of the screen towards you guys, and you have a ring of particles, which aren't just moving up and down like it did in the last case. It's being stretched in one direction and squeezed in the other. And this continues to happen as the gravitational wave goes through it. Okay, so now imagine that all these test particles are photons, or light particles. Well, I already told you that those have a temperature associated with them. But what I haven't told you yet is that they also have electric and magnetic fields. So here, we'd have a photon which is moving like this, and you have the magnetic and electric fields moving with it that are perpendicular to each other, or 90 degrees apart. So to kind of drill this point home a little bit more, I'll show you an animation. So here we have a photon moving from this part of the screen across like that. There's kind of a lot going on, so try to focus on maybe just one of the arrows and look at how the arrow changes as these waves move through it. Another thing you can notice is that it's oriented so one of the waves is straight up and one of the waves is horizontal. But nothing said it had to be that way. As long as the two waves are 90 degrees apart or perpendicular, it can be oriented in any direction you want to. And that orientation is known as polarization. So imagine you have a light source. The light source is going to emit light, some vertically polarized light, some horizontally polarized light, and anything in between. Then you have a polarizer, or in this case, a picket fence. that just has these horizontal holes, these vertical holes in it. So it's only going to allow the vertically polarized light to go through it. Well, this is actually something that you can use in your everyday life if you use polarized sunglasses. So if you have the sun, which will emit light at a bunch of different polarizations, or unpolarized light, and it gets scattered off of some water and becomes partially polarized. Then it goes towards your sunglasses, which are like two small vertical picket fences. It's only going to allow the vertically polarized light to get through it and block off all of the horizontally polarized light, which is actually good because that's glare and it's kind of hard on your eyes. Well, scientists can use the same idea for trying to measure the polarized light from space. So if you have the Big Bang, the light can scatter off of electrons similar to the light scattering off of water and become partially polarized as well. Then we'll have our detectors, which are kind of like having a pair of sunglasses with one vertical picket fence and one horizontal picket fence. This way you can measure how much vertical polarization you have and also how much horizontal polarization you have and see if it matches with your theories or not. Well, you might be thinking, I said that we were going to try to use gravitational waves, and here I'm talking about electron scattering. Well, gravitational waves can also polarize light as well. So if we have light from the Big Bang, we then have gravitational waves produced during inflation, which can polarize the light. And this results in the cosmic microwave background light being partially polarized. We can then measure how much of these different types of polarization we have to figure out how much gravitational waves were actually produced during inflation. When you're talking about the cosmic microwave background, these types of polarizations are called E modes, where in one dimension they'd be straight up and down or just horizontal, and B modes, which are off by 45 degrees. But if you remember, I showed you a picture of the cosmic microwave background that was in 2 dimensions. So in 2 dimensions, these polarization patterns aren't this simple. Instead, they look kind of like these cartoons here, where on the left-hand side, you have B modes, which are these curled polarization patterns, and beside it are E modes, which aren't curled at all. Instead, they just kind of diverge out. Great. So in the cosmic microwave background, what these little cartoons would actually look like is something like this. Where in the top panel, you have all these different divergent patterns everywhere, and in the bottom panel, you have all these curled patterns. So these are actually gravitational wave imprints in the cosmic microwave background. So if we're able to measure these, we'll actually be able to measure these gravitational wave imprints in the uniform field, or the potato salad dinner party that is our universe. But now you might be thinking, I said that the potato salad was like the temperature of these photons, not gravitational waves. Well, when you measure the temperature of the photons, you're measuring the intensity of the light. But we can just slightly change our detectors to also measure how much of these different polarizations we have, not just the overall intensity, to be able to figure out how much gravitational waves actually happened in the early universe. And a lot of people are actually quite interested in this. Here are some of the past, current, and future experiments. This is by no means the full list. These are just some of the notable experiments looking for it. So in the past, we had things like WMAP and Planck, which were satellites in space, Polariz, which is in Chile, BICEP, which was in the South Pole. Currently, we have the South Pole Telescope, which is in the South Pole, CLASS, which is in Chile. And actually, in the next couple of years, we're going to have Simon's Observatory, which is in Chile, LIGHTBIRD, which is going into space, which is an experiment that I work on, and then also PICO, which is going into space. So this is actually, even though this is a super short list of everybody looking for it, quite a lot of scientists are in all these different collaborations, and a lot of people are trying to figure out how much gravitational waves happened in the early universe to figure out how and why the universe looks the way that it does. So just to go back to the takeaway, we have the cosmic microwave background, which is extremely uniform, up to these really small changes in temperature. We can then, using these small changes, try to figure out how much polarization patterns or how much B modes and E modes we have, to then figure out how much gravitational waves are produced in the early universe, to have an idea of how everything started and why it evolved the way that it did to what we see. Thank you.
Thank you, Simran. That was great. All right, we'll take a few questions. right now? Mr. Mark. I should use the throw microphone for now. There you go.
If I remember correctly, in 2014, Bicep thought they saw this. Is that right?
They did think that. Is your question, why did they not actually see it then? Or?
Did they see it or did they?
They didn't. Okay, what happened is when you're in the microwave frequencies, the cosmic microwave background should be the same intensity no matter what frequency you're looking at. But because the cosmic microwave background is so far in the past, there's a lot of things in the way, so there's foregrounds. Even though the CMB will be the same intensity everywhere, the foregrounds will be intense at different spots. So experiments should measure different frequency bands so they can properly take out those foregrounds, like subtract out the galaxy, things like that. Bicep only measured one frequency band, which meant that they thought they could take out more of the foregrounds than they were actually able to take out, which is why they thought they saw these gravitational waves in their signal, but then after having to go through it all again, realized they just didn't properly remove their foregrounds and didn't actually detect them.
All right, we have a young aspiring scientist over here who has a question.
What do the universe look like?
What did it look like?
Yes.
Then or now? Then? Okay. Back then, so at this stage, when it was this old, it basically was a super hot plasma. So kind of like if you think about what you would think like the inside of a star looks like the inside of the sun. There's all these particles that are super, super hot and like hitting off each other everywhere. And that's essentially what the entire universe was like the inside of a star.
Any other questions? People making me want to talk.
What is inflation, or what's the mechanism for it?
Okay, so we don't actually know what the mechanism of inflation is yet. Because we can't directly detect it. So we have tons of theories of how inflation could happen, what particles caused inflation, but we've only been able to rule out some models. Until we can actually measure the gravitational waves, we don't know exactly what it is, but we think it's caused by a scalar field, which, for people that don't know what that means, is basically a particle that's super not common in nature. We've only detected one before, and that took a really long time, like the Higgs boson, if anybody's heard of that. And this particle, what it does is it causes gravity, instead of gravity being attractive and pulling everything in, it causes gravity to be repulsive and push everything out at a really, really fast speeds. And that's also what we think dark energy is, and that's why, since dark energy is taken over in our universe now, the expansion is starting to accelerate again.
All right, I'm going to take my power as chair to ask a question. Simran, you showed all of these telescopes that are trying to detect polarization of the early universe. I have two questions, two-part actually.
Okay.
Why are some in space and some on the ground? And the second question is, the ones that are on the ground, is there a particular reason as to why all of them are in the southern hemisphere?
Okay. Okay, so why some are in space, I'll address first. So we have the atmosphere on Earth, which is actually really not useful for astronomers. It's like in the way. It really messes up the light we try to measure, which is why lots of people love to send satellites to space because the atmosphere is gone. It doesn't matter anymore. But it's really expensive to send something to space, which is why you still build some on the ground. You're kind of lucky when you study the cosmic microwave background because most microwave frequencies can get through the atmosphere, mostly, which means you still can detect them. It's just you still have to do a little bit more work, and that's why, okay, I guess these aren't to scale, but that's why the ground-based telescopes are so much bigger than the satellites we send to space, because they have to be. And then your second part was, why are they all in the southern hemisphere?
Is there a particular reason for it?
I don't think it's necessarily the reason being in the southern hemisphere. I think it's more the places that are chosen because that's where the atmosphere is the nicest for the telescopes, for the light to be able to get through. So things like in deserts, so like Chile, And then the South Pole, so like tundra. Yeah, cold desert. Yeah.
Great. Are there any more questions? All right, let's thank Simran once again.